Welcome. This is information for Unit 4, and in this unit we are looking at correlations and simple regression. And I have an example for us to go over. This example comes from a study I did several years ago with married couples looking at attributions and anger, and something about husbands being schematic and wives being event dependent. So what is this all about? Well, first of all, what are attributions? Attributions have a long line of research, a big literature base looking at attributions, most of it coming out of the area of social psychology. And attributions are simply the explanations, the cognitive thoughts that you have in your mind, the explanations that explain why a person did what he or she did in some situation. You can have attributions for your own behavior. You can have attributions for other people's behavior. So, for example, if someone else did something negative, maybe you had a meeting and someone showed up to your meeting late, you might have thoughts in your mind about why did that person show up late? And those thoughts would be your attributions. You might have internal attributions where you say the person showed up late because of something internal to the person. Maybe the person is lazy or irresponsible. Or maybe you have external attributions. Do you think something external to the person caused that person to show up late? Maybe that person got stuck in traffic. That would be an external attribution. And research in the area shows that when we're making attributions for some kind of negative behavior, we often make external attributions for our own behavior and internal attributions for other people's behavior. Or we can look at blaming attributions. If you explain someone else's behavior, do you have a thought of, well, this person should be blamed for it. This person did something that they're at fault for, and they should be blamed for causing this bad thing to happen. So should they be blamed or not blamed? And in the area of research with couples, we find that attributions are important in terms of what are the attributions that partners make for each other's behavior. If something negative happens, do partners blaming each other? And do they make attributions where they say, well, you caused this negative thing to happen, you're at fault, I blame you for it? Or do they make attributions that excuse each other from blame? Well, you probably had a good reason for it, I understand why you did that, it's probably not really your fault that this happened. And some of that research even shows that if a couple has a habit of making negative blaming attributions, that relationship tends to show declines in relationship satisfaction over time. Whereas you don't see quite so much declines, or at least the declines are less likely if you have a couple that refrains from making blaming attributions and they make more positive attributions for each other's behavior. So those are what attributions are. Now, what I want to do here is look at the relationship between attributions and anger. One of the basic ideas from cognitive theories of emotion is that our feelings are related to what we think. And so if I have a thought, that changes how I feel. And if I change my thoughts, that should change how I feel. And so we would think that if you make negative blaming attributions, if your partner does something, and you blame your partner and think your partner did something bad and your partner's to blame for it, it would make sense you would have a feeling of anger and you would feel angry about that. And a cognitive theory about emotion would say, well, if you change your attributions, if you look at that situation and say, well, wait a minute, let me think about this some more. Well, maybe my partner really isn't to blame for that. Maybe there's a reason why my partner did that. And I don't need to blame my partner for this behavior. That if you change your attribution, there would be a corresponding change in your anger. And actually, there's some approaches to couples therapy that focus on, partly at least, focus on cognitions and things like attributions, with the idea that sometimes couples have relationship distress because they have habits of having negative thinking patterns, and if they can learn to correct their thinking patterns, they can make their relationship better. And part of that idea would be that if someone's making a negative attribution, if we change the way they're thinking, that they would, if they make a negative attribution and they're feeling angry, we change how they're thinking, that supposedly there would be a corresponding change and they would feel less angry. So that's what we want to look at. I want to look at, is there a relationship between attributions and anger? And specifically, if someone changes their attributions, is there a corresponding change in their anger? Now, I've also got this thing about husbands and wives, and we're going to look at data from husbands and data from wives. And the question is, what do we find, say, if we're looking at the correlation between, or the relationship between a change in attributions and a change in anger, would we find a somewhat larger effect in wives and a somewhat smaller effect in husbands? Here's why we might. The idea here is that maybe wives are, for whatever reason, maybe it's part of culture, how they're taught to be, but maybe they're more event dependent when it comes to relationship. That is, they're focused on the here and now. So if a wife is feeling angry, maybe it's because she's focused on what's going on right now in our relationship. And if there's a change in the immediate relationship, I'm focused on that, I attend to that, and that change will influence how I feel about things. So our idea here is that maybe wives are especially attentive to the here and now, what's going on in a relationship. And so if something changes, if they change their thinking, then there would be a corresponding change in their emotion. And that might be an especially strong relationship for wives because they're focused on here and now stuff. The idea maybe is for husbands is that maybe they tend to be a little bit more schematic. Maybe they're not quite so much focused on the here and now events in a relationship. And so they're more focused on just a global appraisal of overall, am I happy in this relationship or am I unhappy? Am I distressed? Is this a good relationship, bad relationship? And so if I think I'm in a good relationship, if I'm happy in my relationship, well, then everything is hunky-dory. And yeah, I'm not angry, and it doesn't really matter what my attributions are. I'm just not angry because I'm happy in my relationship. Or if I'm unhappy in my relationship, if I think, well, I've got a negative relationship, I just globally, it just feels negative. So no matter in this event, maybe you're to blame, maybe you're not, but I'm just angry because I don't like my relationship. So that would be more of a schematic global thing, that their anger is just based on their global feelings about their relationship and not their moment-to-moment appraisals about what's going on here and now. So our basic question here is there a relationship between attribution change and anger change? And would we find an especially strong correlation for wives, and maybe that correlation might not be so strong with husbands? So I have a data set here. This is actually a data set of 77 couples that these couples all came into a laboratory where we asked them to identify an area of conflict in the relationship, and then they were actually video recorded as they spent some time trying to resolve those conflicts. But all of this data actually comes from right before they had that conversation, because before they had that conversation, they identified a topic, some kind of area of conflict in their relationship. And then we asked them, took the wife and husband to separate rooms to complete questionnaires, and we asked them to rate their thoughts about this conflict. So they've identified the conflict. We said, you're about to have this conversation about this area of conflict in your relationship. But before you do that, tell us what you're thinking. Are you making negative attributions? Do you think your partner's to blame for this? Do you think your partner acted selfishly? So we get a measure of their attributions. And then we ask them about their anger. How are you feeling angry? Are you feeling irritated? Are you feeling annoyed about this? How much do you have negative, angry feelings about this conflict? And now we actually, after that happened, they actually did that for one conversation, and then they did another topic and did the exact same thing for a second topic, and then they came back a few weeks later and did a couple more conversations. So we actually had a total of 4 conversations. That allows us to look at the question of change. We can say, how much did the anger change across those 4 conversations, and how much did the attributions change across those 4 conversations? And there's actually some fancy statistical analyses we could actually use. Multi-level modeling would be one way to deal with this type of data set to get at these questions about change across 4 conversations. But that goes way beyond what we have time to talk about now and what I want to deal with. And there's a much simpler way that we can deal with this. It's not quite as fancy and elegant, but actually we get the same results either way. So we will do the simpler approach here. And that is, I'm going to be calculating different scores, and those will be the variables we will be working with. And just arbitrarily, I'm taking 2 conversations, a conversation at time 1 and time 3. That is, they had a total of 4 conversations. I'm taking the first conversation and the third conversation. And I'm taking, we're measuring attributions and anger. And for each one, I'm going to take your attribution score at time 1 minus your attribution score at time 3. So it's not simply what's the level of attributions, but rather to what extent did you change your attributions. So the purpose of using different scores is to get a score that's going to tell me how much someone changed over time. So I'll get your different score for attributions, the extent to which your attributions got better or worse from time 1 to time 3. And then we'll do the same thing for anger, get the difference in anger. What's your anger at time 1, anger at time 3, take anger at time 1 minus anger at time 3. In retrospect, I suppose it might have made more sense to take time 3 minus time 1 because the way I have it, time 1 minus time 3, that means if there's a positive score, your Like if there's a positive attribution, it means your attribution is going down. Or if there's a positive score for anger, it means your anger is going down. Or if you get a negative attribution score, it means it's going up. And that's because the direction of I'm going time 1 minus time 3. If I flipped it around, it would be the other way. So we've got attribution change and anger change. Both these scales I have up on this slide here. They were based on 6 items. So the attribution had 6 questions asking about the extent to which you blamed your partner, thought your partner acted selfishly, thought your partner was responsible for causing some kind of negative problem. And that had good reliability, just right at our threshold for what we might call good reliability, 0.8. And then there was 4 questions measuring how angry people felt. Sometimes I refer to anger as hard emotion, and other places I've called this my hard emotion scale, but it's how much do you feel angry, annoyed, do you feel irritated, things like that. And they had 4 questions measuring those emotions, and that had good reliability. Alpha is 0.9. And so again, we've got attribution change and anger change, and our basic question here is simply, what is the correlation? Is attribution change correlated with your anger change? If your attribution change, if your attributions change goes up, that is you're making, that would actually, if your score is going up, your attributions are going down. But if your score goes up, does the anger change score go up? And if your attribution change goes down, does the two go down together and up together? So what is the correlation between attribution change and anger change? So here is the output for the study, and let's see what we've got here. This is for wives. So I did one analysis for wives and a separate analysis for husbands. And one of the ideas here that was part of the hypothesis was that maybe we might find an especially strong correlation for wives, and then maybe the correlation might be a little bit weaker for husbands. That's one of the things that we can look at here. So we've got a total of 77 wives. We've got our score, so it says A&G DIF13. That stands for anger difference or anger change, the difference between time 1 and time 3. So that's our anger score, or anger difference score, anger change score. And where it says ATT DIF13, that's the change in attributions. Now, one thing to keep in mind in this output is to keep track of what is X and what's Y. So if we start talking about regression relationships where we have one variable is the predictor, the other variable is the outcome, X is our predictor, Y is the outcome. So conceptually, what's the theory here? This is correlational, so we're not actually testing cause and effect, but we have to have a theory about which variable is X and which one is Y. And so in this case, we think that attributions would be X, and the anger change is going to be Y. So anger is Y, attributions are X. So our average on the outcome variable anger change is 0.52 for wives. The average on the X variable attribution change is negative 0.09. We've got the standard deviation for both right there. And let's drop down here to the spot. Here it says correlations. Now this will answer the question right away. What is the correlation between the two? Where it says Pearson correlation. That's our bivariate correlation, 0.55. So actually a large correlation between the two. And right below we have our significance, our p-value. Now this table does not give us a t-test, doesn't give us the output for the t-test. To get that p-value, SPSS did the t-test and ran that t-test and got the t-value. It just doesn't put it in the table, which later on when questions come up and I say, what is the t-value? That means you're always going to have to calculate it because it's not given to you in the output. But SPSS did that t-test and it came up with a p-value that's something less than 0.001. So a very small p-value, meaning that it is significant. So we do have a significant correlation between attribution change and anger change for wives. That is, when wives change their attributions, there is a corresponding change in their anger over time. And it's a fairly large correlation and is significant. We can reject the null hypothesis. What else do we have here? Now in the middle of this page, it says inner item covariance matrix. This is something that often typically isn't part of default output when you're running statistical analyses, but I specifically asked SPSS to put this output here because I will ask you questions about it. And so I wanted to put it there so I could ask you questions about that output. And so this is giving you the variance covariance matrix, where we have on the diagonal are our variances and the off diagonal are our covariances. Recall that if you have variances and everything is turned to standard deviations, everything is turned to z-scores, then your variances will be 1 and your standard deviations will be 1, because the standard deviation of a z-score is 1, and therefore if you take 1 and square it to get your variance, that will be as 1 as well. So if everything is turned to z-scores prior to analysis, your standard deviations will all be 1 and your variances will all be 1. And also know that if you calculate a correlation, but if you calculate a covariance and turn everything to z-scores, that will turn into a correlation. So the thing to note is that you can have a variance, and if you turn everything to z-scores prior to analysis and otherwise get a standardized variance, that variance will be 1. You can calculate a covariance, and if everything is turned to z-scores prior to analysis, that covariance will be a correlation. So a standardized variance is 1, a standardized covariance is your correlation. And we can then make an analogy or a comparison between our variance covariance matrix and the correlation table, because a correlation table is simply a standardized variance covariance table. So a correlation table, what we have is we have two variables. We have attributions, that is our x variable, angers are y, so I've got x and y, and so we could say, what is the correlation between x and y, 0.55, or we do that between y and x. It doesn't matter if you say between x and y or between y and x, it's the same thing. So we've got two correlations that are the same exact correlation. When I talk about a table or a matrix, sometimes we use the phrase a diagonal, and the diagonal is going from the upper left to the lower right. And so we would say that in a correlation table is a mirror image. The upper diagonal is a mirror image of the lower diagonal. The correlation between x and y is the same as the correlation between y and x. So we've got a 0.55 in the upper diagonal and that exact same 0.55 in the lower diagonal. And then on the diagonal, we have 1s. The correlation of x with itself is 1. But note that also that is the standardized variance of x. Because if you standardize any variable, the variance is going to be 1. 1 is always your standardized variance. So you could say x correlated with itself, the correlation between a variable and itself is 1, but also the standardized variance of a variable is 1. So we've got these 1s are always on the diagonal in a correlation table. Now for the variance covariance table, we're going to have unstandardized variances on the diagonal, not the standardized 1s, they're not going to be 1s, but these are going to be the unstandardized variances. And on the off diagonal, or above and below that diagonal, we're going to have the covariances, 0.92. So we've got the variance of x is 1.05, the variance of y is 2.68, and the covariance is 0.92. So there's a very close association between a correlation table and a variance covariance matrix. A correlation table is simply a standardized variance covariance matrix. And normally when we're looking at output, we don't need to do anything with a variance covariance matrix. We typically don't report variances, we report standard deviations, not variances. And we typically report correlations, not covariances, because a covariance is really hard to interpret to know what it means. So we typically don't report the contents of a variance covariance matrix, but I will ask you to do things with it, and I will ask questions about it, so I print it here for you to have for that. Also, I want you to note that when I do print the variance covariance matrix, I have to go to a special spot in SPSS and say, please give me the variance covariance matrix for these variables, and then I put those variables into the matrix and to get the output. And when I do that, I have to click the variables in, and I don't have any system about which one I put in first or which one I put in second. So in this example, I've got attributions, which is x, and anger, which is y. So I put x in first and y in second. But in another example, I might do it reverse. I might put y in first and x in second. And it's not that I'm trying to trick you or do anything tricky. It's just that I didn't have any specific system about which one I put in first and which one I put in second. So whenever you're looking at this type of output, you want to be clear about which variable is x and which one is y, so you know which one we're talking about. And whenever I give you an example on a test or in homework, that will always be made clear. I'll have a theoretical explanation. In this study, we think that this variable a is used to predict this variable y, and I'll make it clear about which variable is a predictor and which variable is the outcome, and so you will know that. And also, actually, well, let's look down the data set. Let's go down a bit further. This is output for the regression analysis. And before we actually look at this output, I might just call your attention to these little footnotes down here, where it says predictors and dependent variable. If you're not sure which variable is x and which one is y, those footnotes will tell you that, because this tells you the predictors is at diff13, so attribution, that's our predictor. The dependent variable, that means our outcome variable, is anger diff13. So if you're not clear what is a predictor and what's the outcome, you could look at these footnotes on the output, and that would tell you that. Okay, let's take a step back here. So what do we see for these regression results for wives? We just looked at the correlation. What about the regression? Well, let's start with the very bottom here. So the very bottom, this is the output where it says B. This is the output for a regression equation with giving us the intercept and the slope. So this is saying our outcome variable y is predicted predicted y is equal to our intercept, which is 0.6. So where it says constant, the constant, it means what is SPSS lingo for the intercept. So where it says constant, that's your intercept. So our intercept is 0.6, and then below it, 0.88, that is our slope. So our outcome variable y is equal to 0.6 plus 0.88 times x, and that will give us our predicted y. So this right here under B, this is our regression equation. One thing to note is that why is that B? So B is kind of for beta. SPSS does kind of funny thing because they have one column labeled B and another column over there labeled beta, and but the one labeled beta above it says standardized coefficients, and above this B it says unstandardized coefficients. And actually both B and beta are the same thing. They're both giving us beta weights, but where it says B, that's giving you the unstandardized, the regular raw score beta weights that have not been standardized. Nothing's been turned to z-scores. So this tells you that a 1 unit increase in attribution change predicts a 0.88 unit increase in anger change. So that's our beta weight right here. And over 0.55, that is our standardized beta. And if you recall, if we turn everything to z-scores prior to analysis, your standardized beta will be identical to a correlation. And indeed, that's what we have here, 0.55. If I flip back to that previous page here, our correlation was 0.55. And going down again, our standardized beta is 0.55. So indeed, those two are the same thing. Which, by the way, I might note that our next unit is going to involve multiple regression. And once we hit multiple regression, that will no longer be true. The standardized beta will no longer be the same as your correlation. But right here, this unit, we're looking at what I would call simple regression, where I have just one predictor and one outcome. And in this example with one predictor, which is all we're looking at in this unit, then your standardized beta will always be the same as your correlation. So for some reason, SPSS chose to label the unstandardized beta B and the standardized coefficient beta beta. I'm not sure why they did. They could have just labeled both beta, but for some reason they said, well, use just the letter B for the unstandardized beta, and we'll spell out the word beta for the standardized coefficient. But they're both betas. The difference is one's standardized, one's not. And so we have our column, here's our betas right there. Then right next to it, it's the standard error of the beta. And we've got a standard error of the beta is 0.15. Right above it, it says 0.16. That's the standard error for the constant. That's the standard error for the intercept, which the intercept does have a standard error. We could say if we do our study over and over again and calculate the intercept every time, how much will that intercept deviate from the true population intercept every time we do our study? And that's the standard error of the intercept. Now, I haven't talked about that before because it's kind of a useless thing, and so we're not going to do anything with it. It's in the output, it's there, but we typically, when we do studies, we typically don't have research questions that we're looking at that are based on the intercept. The intercept is just the number we need in our equation to say what we expect y to be when x is 0. We need to have an intercept in our equation, but we don't have any research questions that we're looking at about the intercept. And so there's no need to calculate a standard error. But if we wanted to, we can, and SPSS gives us that output there. So really, in terms of standard errors, the only one we really care about is the standard error of our beta. We don't really have an interest in the standard error of the intercept. And let's see what else we've got down in this bottom table. There's our standardized beta. We saw that just a moment ago. And then we have t-values. And again, we have a t-value for our intercept and a t-value for our slope. And the t-value for our intercept is 3.78. And again, we don't care about that. That would be for testing the null hypothesis that your intercept is 0. And what your intercept is depends a lot on what your scale is. If you have a scale that goes from, say, 10 to 100, well, then you can't possibly have a score of 0, and so the intercept, of course, is not 0. So whether or not your intercept is 0 or some other number has to do with how you scale things. And of course, if you turn everything to z-scores prior to analysis, if you have z-scores for x and z-scores for y, then your intercept will be 0, because it's always 0 if you have, if everything is z-scores. So whether or not your intercept is 0 or not is basically just depends on how you scale things, how you score things. What your scale is what you use for measuring your variables. And so we have no reason really ever to test the null hypothesis that the intercept is 0. But if we wanted to, again, it is possible, and SPSS gives us this output, our t 3.78, significance 0.000 something. So that's there, but we don't care about that. What we really care about is our slope, the slope for at-diff. And so this bottom line here, including this t-value of 5.69, that is a t-value testing that slope. And that's the t-value we care about, which is the beta, 0.88, divided by its standard error, 0.15, gives us the t-value, 5.69. And that t-value, by the way, would be the same t-value we would get if we calculated the t-value for the correlation. Let's back up to that correlation page. With the correlation output, SPSS doesn't give us the t-value. So if I asked for the t-value here, we'd have to calculate it. But I might mention, by the way, it would be the same value as the t-value for the beta weight. And again, that's because we're doing simple regression with just one predictor. In our next unit, where we do multiple regression, where we have multiple predictors, then the t-value for the beta will be different than the t-value for correlation, because those will start being different things. But for right now, those are both the same thing. So that's our beta weight, our t-value for a beta weight. And then we can also calculate an F table, an ANOVA table, and get the F value and calculate the percent of variance explained. And that's what we have in the middle of the page here. Here's our ANOVA table. And this is just all the values for the ANOVA analysis plugged into the table here. So we have our total sums of squares. So our outcome variable, y variable, is anger diff, and this is the total sums of squares for our outcome variable anger change. And then where it says regression, this is our explained variance sums of squares. Residual, this is our error variance sums of squares. And then we have our degrees of freedom. N-1 is our total degrees of freedom. Number of predictors is our explained variance or regression degrees of freedom. And in this, again, simple regression, we just have one predictor. So in this unit, that's always going to be 1. And then total minus regression gives us the residual degrees of freedom. And then we can take sums of squares divided by degrees of freedom to get mean square. And now we have a mean square numerator, which is 61.48. Divided by mean square denominator 1.9, and that gives us our F value, and then we can determine the significance of our F value. And we'll go back over some of that because I won't want you to calculate that, and I'll review in just a moment again how you would calculate all that. And then we could look at what's our total percent of variance explained. So our regression, that's our explained variance sums of squares, 61.48. Total, that's our total sum of squares, 203.72. 61.48 divided by 203.72, our explained variance divided by total variance, gives us a percent of variance explained, and that is our r squared. So up at this top table where it says r squared, we've explained about 30% of the variance, and that is 61.48 divided by 203.72. That's our explained variance. Next to it, there's a capital letter R. We're not going to do too much with this in this unit. That is simply the square root of your R squared. And in this unit, when we do simple regression, that'll essentially be your correlation, with one notable exception, is that this capital letter R, this stands for a multiple correlation, which is essentially the square root of R squared, and it cannot take on negative values. So if your correlation is negative, capital letter R will be the absolute value of your correlation. So don't report capital R. If you're looking for the correlation, don't look at that capital letter R, because if the correlation is negative, and with a correlation, a negative sign is meaningful because it tells you, is it a positive relationship or a negative relationship? If it's a negative correlation, it means as X goes up, Y goes down, and that's important to know. So the sign on a correlation is important, and with capital letter R, you would lose that sign. So I wouldn't be careful about that. Don't use capital R if you're trying to report a correlation, because you'll lose the sign on it. But otherwise, it's the same thing. Now here SBS has rounded this to 3 decimal places, and it went 0.549, whereas our standard is beta. If I flip to the other page, our correlation was rounded to just 2 decimal places. But it's the same number. If they rounded it out to 3 decimal places for all of these, we would see that it's the exact same number in all 3 cases. And in this case, our beta and our correlation are positive, and so it looks like the same number. But we're not going to do much. We'll do more with that in our next unit, but we're not doing much with that capital R here. There's also an R squared. One of the issues with a multiple correlation and with a percent of variance explained is that it is biased, and there's a correction there. We're not going to do much with that correction here, but if we want to get an unbiased estimate, or an estimate that's less biased, it might not be perfectly unbiased, but a less biased estimate of our correlation, that's what adjusted R squared is. And importantly, we do need this. This is our standard error of the estimate. That tells us how far people's observed scores typically deviate from their predicted values. And that's the standard error of estimate. Okay. Let's real quick take a look and just see what we have for husbands, because one of our hypotheses here is that maybe the effect would be strong for wives, it might be weaker for husbands. And so here is the same sample, but this is the output, this is the results for husbands. And we have all the same things. Here's the descriptive statistics, here's our correlation matrix, and we can jump to the key crux of the matter right here. What is a correlation? Our correlation is 0.19. So a small correlation, our p-value is 0.10, so this is not significant. That p-value is not less than 0.05. So if a p-value is less than 0.05, we say it's significant and reject the null hypothesis. If your p-value is not less than 0.05, and everywhere SPSS says SIG, that stands for your p-value. So for husbands, we actually have a non-significant relationship between attribution change and anger change. Now, of course, keep in mind that if something's not significant, that doesn't mean that there's no relationship. It doesn't mean we found an absence of a relationship. It just means that we failed to reject the null hypothesis. It means that if there is a relationship, our sample size wasn't big enough to detect it. We just failed to detect something if there is anything there. So we have a non-significant relationship, small correlation, not significant. Let's go on and look at the rest of our output here. Percent of variance explained. We've explained 0.03, around 4% with rounding. 0.037 rounds to about 0.04, so we've explained about 4%. And as with wives and husbands, all this output, note that the t-value for the correlation, the t-value for the beta weight are going to be the same, and the p-value, the probability, is going to be the same whether it's the correlation or the beta weight or the f-value. And again, they've rounded here. It says 0.10. Here they've rounded to 3 decimal places. So again, it doesn't quite look the same, but it is. If we were to round everything to 3 decimal places, we would see that the p-value for this f the p-value for our beta weight, and back up on this previous page, the p-value for our correlation, 0.10. It is all the same value because all three of these cases we're looking at the relationship between attribution change and anger change in husbands and the probability of these results if the null hypothesis were true. It's the same probability whether we're looking at it from the perspective of a correlation, a beta weight, or calculating the ANOVA table. So the p-value is the same in all these. And by the way, again, when we do our next unit going on into multiple regression, all this is going to change. For this unit with simple regression with just one predictor, the ANOVA table, the beta weights, the correlations is all looking at the same thing. And our next unit, those are going to be looking at actually 3 different things. And so the ANOVA table and the t-test for the beta weight, the t-test for the correlation will actually be 3 entirely different things, which is actually why we're looking at all 3 of these things here, because it sets us up to understand what those things are and how they can do different things for us in later units. But right now, they're all the same. And here's the beta weight for husbands. Our regression equation says that husbands' outcome, their anger change, is equal to the intercept, negative 0.34, plus a slope, 0.26, times their score on x, their attribution change. And that slope is not significant, but that's what the equation is. Okay, now let's go back. Let's go back to the wives data and their output and look at some of the types of questions that I might ask and things I want you to do with this data. So one question is, right here, what is the typical distance that people's scores and the outcome variable deviated from the mean? And that question should start sounding rather familiar to you. So I've heard that a lot before. That is, again, that same question asking you, what is the standard deviation? And one thing that makes this a little bit tricky is that we're looking for the standard deviation for the outcome variable, the y variable. And so this is one point where you need to be clear about, okay, what is x and what is y? In this case, we're using attribution change to predict anger change. So anger change is the outcome variable, anger change is y. And so we're just asking for anger change, where the standard deviation is 1.64. What's next? Here's another question. My numbers on these slides, I've got 2 and 5. They're not in order, but we will just ignore that part. So we've got, if this study were repeated over and over, how much will the estimated correlation typically deviate from the true population parameter? So you look at that, think, oh, what is that asking for? That is asking for the standard error of the correlation. How far the correlation for a study typically deviates from the true population parameter. That's the standard error of the correlation. And I have that little note there. It says, note, this requires a calculation, and indeed it does. How would we get that? And this is a thing that SPSS gives us the correlation here, but it doesn't give us the standard error of the correlation, and it also doesn't give us a t-value. So if I ask you questions about that, we'd have to calculate it. How do we do that? Well, here I've got the formula here we call the standard error of the correlation. It's a square root of 1 minus r squared divided by n minus 2. So I can just plug that in. Our correlation is 0.55, so plug that in there. Our sample size, if you recall from that table that's showing our descriptive statistics, our sample size was 77. Plug that in there. And I carried it out just to make sure we're really precise here. 0.0964365. And actually, I think even that's a bit rounded. But anyway, so if I take that, so that is our standard error of the correlation. And if we wanted to, if I asked you then to calculate the t-value, you could calculate the t-test from that. So we take our standard error of the correlation, and our correlation and a t-value is always a statistic divided by its standard error. So our statistic is 0.55. Again, our t-value 0.55. Our standard error was 0.096 and so forth, and plug that in there, and I get a t-value of 5.703. And there's our t-value. Which, by the way, note that that came out slightly different from down here. And again, that's just due to rounding. But if we hadn't rounded, if we weren't dealing with rounded numbers, and I on this previous page, I carry this out several decimal places to try to be accurate there. But I'm starting off with this 0.55 as a rounded correlation there. So even that's rounded to begin with. And so right from the get-go, I've got rounded values here. So the reason why, if I calculate it this way, I get a different value is not because the values are different. It's just because, in this case, I'm dealing with that rounded 0.55. And in this output down here, SPSS is calculating this t precisely without rounded values. So they got just a slightly different t value, but that's just due to rounding. And again, if we go back here, if I gave you this information, say, here, you calculate what that t value is, then use what you're given, and I would assume you'd get the t value based on what you were given for it. Let's see some other things, and you can see my numbers are jumping around here. But this is what I call number 1. In solving a regression equation, the computer attempts to make a certain value as small as possible. In the printed results, what number is this minimized value? And recall that when we do regression, we're going to minimize the error sums of squares. And SPSS calls that the residual. So right here, this residual sums of squares, 142.24, that is that minimized value. That's the thing that SPSS makes as small as possible, or you can make as small as possible if you simply calculate the intercept and slope and get our regression equation. What else do we have here? We have this one here. What is the typical distance that people scores on the outcome variable deviated from the regression slope? Typical distance that people score is deviated from the regression slope, and the regression slope gives people's predicted values. So this question is asking the same thing as, what is the typical distance that scores deviated from their predicted values? And what tells you that? What tells you how far scores deviate from the predicted values? Well, that's the standard error of estimate. And so that's right up here. The standard error of estimate is 1.377. So the answer to that is the standard error of estimate, 1.377. Let's see. And then we have this question here. If this study were repeated over and over, how much will the estimated unstandardized beta typically deviate from the true population parameter? So that's asking for the standard error of beta. How much will the beta typically deviate from the population parameter? That's the standard error of the beta weight. And that's given right in here. 0.15 is our standard error of the beta. What else? Some more questions here. Next question. What is the percent of variance that has been explained in this equation? Well, the r squared is a percent of variance that's explained, which is right here, r squared 0.30. And this is for our wives. Again, we've explained 30% of the variance in the outcome variable for wives. And if I scribble that out, you could simply take your regression sums of squares, your explained variance sums of squares, divided by your total, and you would get your percent of variance explained that way as well. But if it's given to you, don't bother calculating, just to get it right off the page. Next question. What is the expected increase in y if there is a 1 unit increase in x? Well, that's asking for the beta weight. The beta weight tells you how much y goes up, or y is expected to go up if x goes up by 1 unit. And our beta weight is 0.88. So that's the answer to that question. 0.88, that's the expected increase in y given a 1 unit increase in x. Let's see. Finally, on this page, we have what is the expected value for y when x equals 0? Well, that's asking you for the slope. What is the slope? The slope is where it says constant. That's 0.6. That's the expected value for y when x equals 0. Let's see. Now, here's some things. I've got some equations on this page, and there might be a situation where I say, what is this equation? So, for example, we've got this equation at the top here. I say, what is sum of x minus x bar times y minus y bar divided by n minus 1? And so the first step is to figure out, well, what is that? Sum of x minus x bar times y minus y bar divided by n minus 1. Well, that numerator is our sum of cross products divided by n minus 1, and that's going to give us a covariance. So that question is essentially saying, what is the covariance between x and y? And so to get that, we can go, here's our variance covariance matrix, and our covariance is 0.92. So to answer that, 0.92 is our covariance. And the covariance is the sum of cross products divided by n minus 1. What else do I have here? I have over here, what is the sum of y minus y bar squared? Well, that is simply the sum of squares for y, which would be the very first step in calculating the standard deviation. If we calculate standard deviation, we first calculate the sum of squares. And then actually, if you note on this other thing, then we divide by degrees of freedom. So this is going to be the variance right there. But I'm jumping ahead of myself. First step, calculate the sums of squares for y. Where can I get that? Well, right down here in our ANOVA table, 203.72, that is the sums of squares for our outcome variable y. So that's right there, 203.72, the sums of squares. And then we can take it to the next step. What is our sums of squares divided by degrees of freedom, which is the same thing as our variance? What is our variance? And you could take 203.72 divided by our degrees of freedom, n minus 1, 77 minus 1. Or you could simply look at our variance covariance matrix here. Now we want to keep track again, what is x and what is y? So attribution, that's our x variable. Anger is our y variable. And so right here, 2.68, that is the variance for y. So we didn't even have to calculate anything because it's right there. There's our variance for y. Or if we wanted to, we could go and look at our anger change. Here's anger change y. And here's our standard deviation for anger change. And we could take our standard deviation and square it. And that would give us our variance as well. So there's actually a few different ways you could get at that same thing. Although simplest is just go to your variance covariance matrix. It's printed right there for you. You don't have to calculate anything. So that would be the ideal way to do it. Just get it off your variance covariance table. Here are some other types of questions I might ask. So in this example, what I'm going to do is I'm going to give you someone's score. And now in this, I've switched back to husband's output here. We were dealing with wives' output for a while. Let's look at husband's output. And here's our regression equation for husbands. And this wasn't significant, but we can still plug our equation in and get people's predicted scores on it. So our slope, or our intercept was negative 0.34, and our slope was 0.26. And so what I'm going to do is I'm going to say we have someone in this sample, maybe someone named Joe, and Joe gets a score of 0.8 on X. So if X equals 0.8, what is that person's predicted score? So someone is in the sample, they get a score of 0.8 on the X variable, that's the attribution change variable. What is their predicted anger change for that person? So we can plug in our equation here. So y hat, that's the predicted score on y. And we plug in our equation, or our intercept is negative 0.34, right there, there's our intercept, negative 0.34. Our slope is 0.26, so I put that right there, 0.26. There's our slope. This person had a score of 0.8, so I put that right there. Intercept plus slope times x, I get this person's predicted score of negative 0.132. That's that person's predicted score given our equation, given our equation that we have in our output, and given that they got a score of 0.8 on x, that's their predicted score on y. Now, let's add to that. So I just figured out this person, if they get a score of 0.8, that their predicted y is negative 1.32. We just figured that out. I'm going to ask a few more questions about that. So I'm going to say, okay, I gave you x. I said this person's score on x was 0.08. I just told you that. But now I'm going to tell you what their actual score on y. Say they actually got a score of negative 0.5. See, that's what they actually got. So we predicted they would get a score of negative 1.32, but they actually got a score of 0.5. So if that was the case, I just gave you what their score is on y. Now you can tell me what is the squared error for this person. So we take their observed score, they got a score of negative 0.5, and their predicted score, we predict they should have gotten negative 0.132. We take observed minus predicted, and then square it to get the squared error. And for that person, their squared error is 0.1354. That is the squared error for this particular individual who got a score of 0.8 on X and 0.05 on Y, and we're using this regression equation. And that, given all that, plugging it in, that's that person's squared error. Okay, let's ask a few more questions about squared error. So I can ask this question. We just calculated the squared error for one particular person in this sample. We got this one person squared error. Now I'm going to ask, what is a typical squared error for participants in the study? On average, what is a usual squared error for most people? And that's from our ANOVA table here, this mean squared error, or mean squared regression, which is the same thing as mean squared error, is 1.76. That is our mean squared error. That is the typical amount of error, typical amount of squared error that people will make in the study. Then I'm going to ask, what is the sum of squared error for all participants in the study? What is the sum of the squared errors? And that's over here, our sum of squared error, or the sum of residual. SPSS calls our errors residual. So the sum of squares residual, which is the same as the sum of squared error, and that's 132.28. That would answer that question, 132.28. What else? I might ask you to calculate the correlation. So we saw our output. We saw that the correlation is 0.55. But what if I just gave you, say, you had this variance-covariance table. I gave you that, and I said, now you calculate the correlation. You tell me what the correlation is. And so if you wanted to do that, we need to get the covariance. In this case, it's 0.92. Our covariance is 0.92. Divided by the standard deviation of X times the standard deviation of Y. Correlation is a covariance divided by a measure of averaged variance. And we calculate the average variance by taking our two variances and taking the square root of each, which turns them into a standard deviation, and then multiplying them together to get a measure of averaged variance. So correlation is a covariance divided by the product of your two standard deviations. So I've got 1.64 and 1.03. We plug those in down here. The covariance divided by the product of our two standard deviations, and that would give you the correlation. Which, by the way, just realized I've switched back to Y's output again here. So that would give us that 0.55 correlation we've been looking at. Or I could say calculate the beta. So here, calculate the beta. And recall that the formula for a correlation and the formula for a beta is very similar. The correlation is a covariance divided by a measure of average variance, which is the product of two standard deviations. A beta is simply a covariance divided by the variance of X. You're not averaging variances of X and Y, it's just the covariance divided by the variance of X, which is the squared standard deviation of X. And you can get the variances from the variance covariance table, or actually in this example, I guess I got it up here from my standard deviation, and I squared it. So I take my covariance, 0.92, divided by the squared standard deviation of X. Or if I wanted to, I could have just gotten here as our variance of X, attributions is X, so I could have taken 1.05, which actually in this case, 1.03 squared is 1.05. Very, very similar numbers because we're very close to 1 there. But you could do it either way. You could get your standard deviation and square it, or you could get it from the variance covariance table and just get the variance that way. But to get beta, take the covariance divided by the variance of X, and you will have your beta. By the way, also, if I ask you, another thing I might ask you is to calculate the standardized beta. If I say here's our standardized beta 0.5, if I ask you to calculate the standardized beta, the thing to keep in mind here is that in this unit where we're doing simple regression, we have one predictor. Your standardized beta is always the same thing as your correlation. So if I ask you for the standardized beta, just go and get your correlation, or if you need to calculate your correlation, and know that that is also your standardized beta. What else? Let's see, I can also ask you to calculate the intercept. What is the intercept? We see down here our intercept, or what SPSS calls a constant, is 0.60. And so the first thing I need to do is get the mean of Y. The mean of Y is 0.52 minus my slope, 0.88, times the mean of X. and that will give us our intercept, which is 0.60. Let's see. Then at this point, we could calculate a t-value. We could calculate the t-value for our beta weight. Right here, here's our beta is 0.88, and a t-value is always a statistic divided by its standard error. So we can take our statistic, our beta weight 0.88, divided by its standard error, and I have it down in this formula down here, 0.88 divided by its standard error, and I get 5.8667, which is just a little bit different from what's printed in this output here. And again, that's simply due to rounding. If we were using precise beta weights, if it was not, we've got 0.88, if we've carried it out and got the exact beta weight and exact standard error and plugged it in, we would get identical values in our calculation that we get in the table up here. But it's a little bit different because we've got rounding going on, so we didn't get exactly the same value. We could also calculate the t-value for our correlation. And here we've got our correlation was 0.55. Down at the bottom, we have that formula for the standard error of the correlation, 1 minus 0.55 squared divided by n minus 2. And again, our t-value is 5.7032. And again, note that these are all just a little bit different because of rounding. What else? Well, actually, another thing I might do is here we have this ANOVA table. I could just give you these two values that are in the box. I could give you the total sums of squares and the residual sums of squares. And then I could also let you know, give you the output that shows that our sample size, we've got 77 people in the sample. And based on just that, you've got the total sums of squares, the residual sums of squares. We know our sample size is 77. Based on that alone, you could reconstruct the rest of that ANOVA table. So we could get the regression or explained variance sums of squares, which is 61.48. You just take total minus residual. Total minus residual will give us the explained variance sums of squares. In other words, the total minus error sums of squares gives us the regression or explained variance sums of squares. And then once we have that, we can then go and calculate degrees of freedom. We know that our total degrees of freedom is going to be n minus 1. We have 77 people, so n minus 1 gives us 76 degrees of freedom. We know the degrees of freedom for our explained variance for regression sums of squares is equal to the number of predictors. And with simple regression, it's always just going to be one predictor. In our next unit, we'll have more than one predictor, but for now, everything's going to be just one predictor, so we have 1 degree of freedom. And then take our total regression degrees of freedom minus our regression degrees of freedom, total degrees of freedom minus explained variance degrees of freedom to get our error or residual degrees of freedom. 76 minus 1 gives us 75. So now we've got all of our degrees of freedom. And now we can take our sums of squares divided by degrees of freedom to get mean square. So 61.48 divided by 1 gives us 61.48. Which with simple regression, we just get the same value. When we go on to multiple regression and we have degrees of freedom that are larger than 1, then that can give us different things. Then we'll take our error, our residual sums of squares, divided by degrees of freedom, 142.24, divided by 75, gives us our mean square, 1.9. So our mean square error, our mean square residual is 1.9. And now we can calculate our F value. We take our mean square explained variance, 61.48, divided by our mean square residual, 1.9, and that gives us our F value, which is 32.42. And so now we've reconstructed this entire ANOVA table just from knowing the total and residual sums of squares and our sample size. What else? I could just ask you, what is the variance of y? And actually, we've done this already in a previous question where I gave you the formula for variance of y and asked you, what is this? Or I could just simply ask, what is the variance of y? And we again would do it the same way. We have our, just from the ANOVA table, you can get that. You can take, here's our total sums of squares. We know our sample size is 77. So sums of squares divided by our degrees of freedom, 77 minus 1. Sums of squares divided by degrees of freedom will give us our variance. So just from the information we have right here, we can calculate what our variance is, which is 2.68. And then if I said, well, what's the standard deviation of y? You just take the square root of that, and we get a standard deviation of 1.64. And I could say, what is the standard error of estimate? Let me back up and so we can see all of our output here. So for example, for y's, this is showing all the output right up here. Standard error of estimate 1.377. So that value right there is the standard error of estimate. So it's given in the output. And now I'm going to go back to this slide we were just looking at here. Oh, there we go. But now I've blocked it out. You don't see it. I'm asking you, what is that value? Well, it's very easy to get from your ANOVA table, because the residual 1.9 here, that 1.9 is the mean squared residual, or mean squared error. It's the typical squared error. And to go from the mean squared error to the standard error of estimate, we just take the square root. The standard error of estimate is simply the square root of your mean squared error. So I just simply take 1.9 and take the square root of that, and I get 1.38. And so I can calculate the standard error of estimate just from my ANOVA table. And then we could look up p-values. And now we can look up p-values for correlations and beta weights, or we can look beta weights using a t-test. And we've already seen in a previous unit how to use a t-table. And you just need to keep track of what your degrees of freedom are. With a correlation, your degrees of freedom are going to be n minus 2. And so you could go to get your t-value from a correlation and look up the probability of that t-value from a t-table with n minus 2 degrees of freedom. But we haven't looked at an example of how do you get a p-value for an f-test. If you get your ANOVA here, and we got an f-value of, say, 32.42, and we want to know what is the p-value, maybe I scribble it out, and I say, you tell me, what is the p-value? And just like the t-test, you're not going to be able to give me a precise p-value. Well, if you go online and get one of those calculators, just like there's calculators for t-tests, there's calculators for f-tables, and you could go online or get an app for an F calculator and plug that in and give me a precise value. But on tests and homeworks, the plan will be I'll give you the table, and I'll have you look up F values on a table. And it'll be the same as with a T value, where you can't give me the precise value. We'll be using inequality. So we'll be asking the question, is it significant? Is it less than 0.05? And so forth. And now, one thing to note is that when we looked at a t-table, we had just a single degrees of freedom. But for f, we have 2 degrees of freedom. We have a degrees of freedom for our numerator and a degrees of freedom for our denominator. So I'd say it this way. We have an f, degrees of freedom of 1 and 75. And when giving degrees of freedom for an f statistic, it's just tradition. We always give the numerator first and the denominator second. So I'd always say we have 1 and 75 degrees of freedom. So we want to note what's our degrees of freedom and then go to the F table to see if our value, we got an F value of 32.42, and we want to know, is that significant, or what is the p-value there? So here is an F table. Now, when we were looking at the t-test and the t-tables, we had a separate column. We had one column for p is less than 0.05, another column for like p is less than 0.01, and one for p is less than 0.001, and that type of thing. We had a separate column for every p-value, or a different set of critical values. For an F table, it's going to be a separate page for every critical value. So here is the first page of an F table, and this entire page is for alpha equals 0.05. In other words, this entire page is giving us critical values for saying p is less than 0.05. So in our example, we had an f. Our F value was 32.42. Our degrees of freedom are 1 and 75. So I need to look up, it's maybe hard to read. This says degrees of freedom numerator. That's what it says across the top. That says degrees of freedom numerator. And then along the side, this says degrees of freedom denominator. And so what we want to do is find the point on this table, the cell that goes with 1 degree of freedom in the numerator, as we have 1 degree of freedom in the numerator, and 75 degrees of freedom in the denominator. Now, as before with t-tables, we'll have to do some rounding because there's not a specific row for 75. If you see really close here, this actually says a 60. Then it goes from 60 to 120. As with the t-table, we're always going to round down, never round up, always round down. So I'm going to use the row here where it says 60. So if I look for 1 degree of freedom here, my 60 here, and the value right there, I zoomed in, this picture right here, just a zooming in of what you see at the left here. We've got 60 degrees of freedom in our denominator. That critical value says 4.0. So how to read that is the critical value for F. If you have 1 degree of freedom in the numerator, 75 or rounding to 60 degrees of freedom in the denominator, our critical value is 4.0. And if our F exceeds 4.0, then we can say P is less than 0.05. If our F fails to exceed 4.0, then our results are not significant, and we cannot say P is less than 0.05. We can say P is greater than 0.05, which would make it non-significant. So, in this example, we got an F of 32.42. That is indeed greater than 4.0. So, we can say this is significant. We can reject the null hypothesis. We say P is less than 0.05. P is less than 0.05. And that's all we can do for this page. Now we want to be a little more precise. Well, can we say something more stringent? Can we say P is less than, for example, can we say P is less than 0.025? And so now I flip to this next page, and this entire page is giving us critical values, and at the top it says alpha equals 0.025. That means we're giving critical values for the 0.025 to be able to say, is P less than 0.025? Again, we have 1 degree of freedom in our numerator. We're going to round down to 60 in our denominator. Our critical value is 5.29. Again, I've zoomed in over here so you can see 5.29. That's our critical value. And so our value, 32.42, did indeed exceeded our critical value. It's larger than 5.29. And so because our F exceeded the critical value, we can say indeed P is less than 0.025. So P is less than 0.025. Let's flip the page. Let's keep on going. As long as we keep getting significant things, we'll keep on going. So this page is for alpha 0.01. So this is going to allow us to determine the probability, or say, is P less than 0.01? Is this something that would happen less than once in 100 times? Our critical value, zoomed in here, is 7.08. With 1 in 75 degrees of freedom, our critical value is 7.08. And our F, 32.42, exceeds that critical value. So we can say P is less than 0.01. And that is actually how far that table goes. I've flipped onto my next slide here. So we really only have those options. If it gave us another table, maybe we'd go on more than that, but that's where we stop. So, and then we can say P is less than 0.01. And that is everything I wanted to do with that set of output for wives and husbands. This slide here has another type of question that I might give you, and this is where I'm giving you a very small data set and asking some questions about it. So let's see how this example goes. And I got a couple different ways I might set this up. And these are examples where I want you to work with a data set to show you understand basically the mechanics of how regression is working, and how if we have a set of scores, how we go about calculating predicted scores and residuals or error scores for every person in our data set, and how all that works. So let's see what we have here. So I'm giving you an example. I say in this example we have 5 people rated the extent to which, how much they like peas is X, and the extent to which they like pigs is Y. So I don't know, maybe people who like to eat peas also like, and I guess here I didn't clarify if they like to eat pigs like pork, or do they like pigs as pets. Maybe we'll say they like pigs as pets. So if you like to eat pigs, do you like to have pigs as pets? That can start to be a tongue twister if I say that too fast. But to what extent is liking peas related to liking pigs? Peas is X and pigs is Y. And so maybe I have a study and I give people a questionnaire. Maybe one questionnaire measures how much you like peas, and I have another scale that measures how much you like pigs, and I get scores for both. And say I do the study, and I have just a very small sample. I have 5 people. I have Cal, Deb, Eve, Fave, and Gus. I have just 5 people in my data set. And they take my questionnaire, I get their scores for how much each of these 5 people, how much they like peas, and I get their score for how much they like pigs. And I run a regression, and my beta weight, or my intercept, beta naught, is 5.2. My slope is 0.4. The mean of y is 8.4, and the standard deviation of y, which I wanted to be a little precise here to make everything work out, is 2.3022. So there's the information. I've given you this information. Now, one thing I might ask is I say to give the predicted score for every person in the sample. So I've got 5 people. I've got Cal, Deb, Eve, Fave. And so I might say, what is the predicted pig liking score? That's the outcome variable. The outcome variable is how much they like pigs, is y. So what is the predicted y for Cal? What's the predicted y for Deb? What's the predicted y for Eve? And predicted y for Faye and for Gus? So I might want you to give me the predicted y for every single person in the sample. So here on this slide, I show you how to do that, as well as some other future steps that we will do in a moment here. But to get someone's predicted score, at the top, I have the basic equation where it says your predicted score, y hat is your predicted score, is equal to the intercept plus slope times x. And I've told you that our slope is 5.2, and I've told you that the intercept is 5.2, and that the slope is 0.4. So predicted y is equal to 0.52 plus 0.4 times x. And just to make this calculation easy, I mean, you could there's many different ways you might want to set it up if you're doing this on your own. Just to lay it out and see how it's done, it was easy for me just to write the slope and the intercept into the table right here. So down here, here's what I gave you. I gave their x scores, how much they like peas. Their scores for x are right there, 3, 7, 9, 10, and 11. And then I just wrote the intercept, 5.2. I just plugged that in right here. And I just wrote it the same for everyone because it's the same. The intercept is parameter estimate. It's the same for everyone. And then I wrote the slope right here, 0.4, 0.4, 0.4, 0.4. And this made it very easy for me just to set up, because I can just now take your intercept plus slope, 0.4, times x, 0.3. And for the first person, that was 6.4. Take the second person. The intercept, 0.52, plus the slope, 0.4, times x, 7, and I get 8. Third person, intercept, 5.2, plus slope, 0.4, times x, 9, I get 8.8, and so forth. So I can calculate every single person's predicted score. And now I've got the 5 predicted scores for Cal, Deb, Eve, Fave, and Gus. I've got all their predicted scores, 0.64, 0.8, 0.88, 0.92, and 0.96. So there's their predicted scores. Now, once I have that, I might say, oh, let's do some more stuff, which you would be very excited to know, because you think that'd be kind of boring just to stop right there, because we can do more stuff. So let's do more stuff. I might say, tell me, what is the sum of the squares for the explained variance? What's the explained variance sums of squares? And you can figure that out. We can just take this a few steps further. So we just calculated every person's predicted score on y. So now if we want to get the sums of squares explained variance, recall that the explained variance, the explained variance sums of squares, the formula for that is how far, which I have done right here, it's your predicted y minus the mean of y for every person and squared, and sum that up, and that will give us a sum of squared for explained variance. So I want to get your predicted y minus the mean of y, and then square it and add it up, and I will get the sum of squared explained variance. So I'll do that here. I've got every person's predicted y right here, and I'll take their predicted y minus the mean of y, and I've told you up here the mean of y is 8.4. So that's been given to you. I told you the mean of y is 8.4. If I didn't tell you that, you couldn't figure this out. But because I've told you the mean of y is 8.4, we can proceed, we can figure that out. So I take 6.4 minus 8.4, and I get negative 2. 8 minus 8.4, and I get negative 0.4, and so forth. So I calculate every person's y hat minus y bar. And now I need to simply square those values. So I take that difference, 2 squared, I get 4. Negative 0.4 squared, I get 0.16. Again, 0.4 squared, I get 0.16. 0.8 squared, I get 0.64, and so forth. And then I'll simply sum those squares. 4 plus 0.16 plus 0.16 plus 0.64 plus 1.44, add it all up. Those should be plus signs, but I could do plus, plus, plus. I'm just adding it all up. And the sum sums to 6.4. That is my sum of squares for the explained variance. Now I might say, okay, we've got the sum of squares explained variance. We might move towards saying, well, what is the percent of variance explained? And to do that, we take the total explained variance divided by the explained variance divided by the total variance. And so to do that, you'd have to figure out what the total variance is. What is the total variance in y? Well, I tell you right over here that the standard deviation of y is 2.3022. And so if we take that standard deviation and we square it, we'll have a variance. And if we multiply that by our degrees of freedom, we will have our sums of squares. And we can calculate our degrees of freedom. Degrees of freedom are n minus 1. And we can just count. We got 5 people, so our sample size is 5 people. So our degrees of freedom are 4. N minus 1 is 4. So I plug that in. I take my, here's my standard deviation squared times my degrees of freedom, and I get a total sums of squares of 21.2. So now we can go ahead and calculate what is the percent of variance explained. We have my explained variance, 6.4, divided by the total sums of squares variance, 20.2, and we've explained about 30%, 0.302, around 30% of the variance has been explained in this example. Okay, let's keep the same data set, but let's switch things around. Say I get you a little bit different information here, and I might ask some different questions. So still the same 5 people, Cal, Deb, Eve, Faye, and Gus, still have the same people, still have how much they like peas, predicting how much they like pigs. But what I've done here is I've actually went ahead and I gave you their actual scores on y. So the previous example, I didn't tell you what their actual scores were on the y variable, on how much they liked pigs. But here, I actually tell you how much they like pigs. So I get to, Cal had a score of 6, and Deb had a score of 9, and Eve had a score of 7, and so forth. So I have both scores on X and scores on Y are given in this, this table here. And, and you could calculate what predicted Y is, but I've given that to you as well. And in our last example, we went ahead and calculated that. But assuming I gave you the intercept and slope and all that information. But here I went ahead and put that in, and it's already given to you, so you don't have to calculate it here. So I've given you the X and the Y and the predicted Y for every single person. And now what I'm going to ask you, you see at the bottom of the page, what are the residuals for every single person in the data set? What's the residual score for Cal? What's the residual score for Deb? And one of the key things that I want to make sure everyone's aware of is that when you do regression, every single person, every single case will have a residual score. And we can calculate what everybody's residual score is. So let's do that. And to get the residual, or the E or the error stands for residual, is simply your observed score minus predicted. Y minus Y hat. Observed minus predicted. So if I take your score on Y minus predicted Y, I will get the E, or the residual. So I've got a column right here to give everyone's residual. I take 6 minus 6.4, and I get negative 0.4. 9 minus 8, and I get 1. 7 minus 8.8, and I get negative 1.8, and so forth. So I take everyone's observed score, subtract the predicted score from it, and I get their residual. And now I have calculated everybody's residual. As you can see, I've got another column there for residual squared, which probably gives you a hint we're going to go on and do some other things, and indeed we are. Because I can at this point ask, okay, what is the sum of the squared error? So a moment ago in the previous little bit, we were looking at how you could calculate the sum of squared explained variance. Now I'm asking you, what is the sum of squared error variance? And so at this point, we can take our residuals and square them. So negative 0.4 squared gives us 0.16. 1 squared gives us 1. negative 1.8 squared gives us 3.24, and so forth. So I calculate, take each error, I square it, and then I add up all 5 of these squared errors, add up everything in that column, and I get a sum of squared error of 14.8. Now at this point I might, if I wanted to, I might ask you, or I could do this at any point, I suppose I don't have to do it at this point, but one of the things I might ask you is, and this is actually, I suppose, going back a bit here, we calculated this error for every single person, and we have every single person's correlation on the Y, how much they like pigs. So every single person has a score on Y, how much they like pigs. Every single person has a score on air. And I might say, what is the correlation between Y and E, between your score on Y and the air? And ask you, tell me what that correlation is. Now, if you're feeling a bit sleepy and not thinking about it and not paying attention, you might think, oh, okay, I got to calculate the correlation, got to pull out my formula, I got to calculate a covariance and divide the covariance by the product of two standard deviations, and okay, I need to calculate the standard deviation of X or of Y, calculate the standard deviation of E, calculate the covariance and so forth, and you're figuring and so forth and doing all that stuff, and that is totally unnecessary. You should not have to do a bit of work to answer that question, because I want to make sure everyone's aware of the basic principle here that the correlation between E and Y will always be 0. Once you've done that process and extracted out the residuals for every single person, once you've got a residual score for every single person, if you've extracted those residuals out, those residuals, by definition, by the mathematical process you've used, those residuals have to be correlated 0 with Y. So if we actually did a correlation between these errors and these Y squares, if we did a correlation between these two columns, that correlation would be exactly 0. It always has to be. So if I ever ask you what is the correlation between Y and the residuals, you don't have to do any calculation. The answer is always going to be 0. Okay, let's get back to, we've calculated our sum of squared error, and from this point we could go on and calculate the percent of variance explained, just as we did before. Now, we saw before that if I give you the standard deviation, we could calculate what the sum of squares total is. And now at this point, we could calculate the explained variance by subtraction. So if we've already got the sum of squares total, and this is that same sum of squares total I showed you before, you could do that. If I gave you the standard deviation, you could plug that in and figure that out, like we saw before. So if we take our total sums of squares, 21.2, minus our error sums of squares, we would get our explained variance sums of squares, and that's what we see up here. So I'm taking my total variance sums of squares, which is 21.2. My error variance sums of squares was 14.8, and that gives me explained variance of 6.4. So there's kind of two ways we can get the explained. We can calculate the explained variance directly, or we could calculate the error sums of squares and then use subtraction to get at the explained variance. Two paths to get at the same thing. And then once again, we can take our explained variance sums of squares divided by our total, 6.4, to get our percent of variance explained, which is the same value we got when we did this previously, because this is all part of the same data set and these numbers are all the same. And that is everything for this unit, with I guess one final slide where I didn't know where to put this anywhere else, so I just stuck it at the end here, where I tried to make the large bunny attacking the Monty Python group. And that's the end of information for this unit.